Should I start recording or okay? So students, so this is our home page and welcome to 4PiAcademy, and you guys know that I'm your instructor now for thermodynamics classes, and we will start today thermodynamics as well. So am I loud and clear? Can you guys hear me properly?
Yes, ma'am.
Okay. If in mid between, if you guys can't hear or my screen is not visible, please unmute your mic and tell me. Okay. So should we start? Okay, I'm starting. So okay, so a brief about me. This is Monika Shrivastav. Maybe you guys know me earlier because some of my lectures are on the website of classical mechanics also. And today we will start with thermodynamics. So first of all, what is thermodynamics? So basically we know that thermodynamics is that subject in which we deal with the temperature, work, heat, energy of system, etc., etc. And just we study about three laws of thermodynamics: zeroth law, first law, and second law. But thermodynamics is not just this. Thermodynamics is a vast area in which we can study all about the molecules, all about their kinetics, all about the heat, all about the temperature, all about their thermodynamic function, and so on. So basically, this is the syllabus of NET of thermodynamics. Thermodynamics and statistical physics both are categorized in one group. So in this syllabus, we have to read all these laws of thermodynamics and their consequences, thermodynamics potentials, and this all. And it is thermodynamics and statistical physics, first and second order phase transitions, diamagnetism, paramagnetism, ferromagnetism, Ising model, etc. So this is all what we will read in upcoming lectures one by one. And this is syllabus of GET, in which there are sections divided, some basic concepts, and then laws of thermodynamics, and then properties, and then thermodynamic relations, and then thermodynamic cycles and ideal gas mixtures. So these are some topics for the exam of GET. So basically this is the total syllabus. And these books I'll suggest you guys to follow. Thermodynamics and Statistical Physics by F. Reed. This is a standard book and a very good book to study about thermodynamics from basics to the advanced. And then second one is Thermodynamics and Statistical Physics by Gupta Kumar. This book is already on our website. And then these are some books. And the fourth and fifth book, Concepts in Thermal Physics by Stephen Blundell, Volume 1 and Volume 2, soon will be uploaded on the website. So you guys can check these books too. Okay, so we will start with the basics of thermodynamics. The thermodynamics is based only on three things: heat, temperature, and work. So basically, heat and temperature are two different things. Some people can say temperature is a type of heat, or heat can be correlated by temperature, but no, it is not like that. Heat and temperature are very different things. So let's know how. Mechanics is a branch of physics in which what we study, we will be studying about velocity, acceleration, energy, momentum, position, etc. But we never study in mechanics about a temperature or temperature function, or about the diamagnetic or magnetizing behavior due to temperature and due to heat, and types of heat generation, heat transferring, etc. So mechanics is a different branch and thermodynamics is different branch. Both are the parts of classical physics. Okay, classical means the physics which which Newton used to follow, Sir Newton used to follow. Okay, so a question is, what happens to the energy of a ball when we drop it on the floor? You guys know that a ball has its energy and we are dropping it, it has the kinetic energy. But when it's stuck to the floor, where is the energy gone? What happened to the energy of ball? So the answer is it goes into heat energy. The kinetic energy is converted now, and when the ball is stuck to the floor, some heat energy is generated. So now another question arises, what is heat energy? Okay, so what is heat energy, and let's start now. The answer is a bit longer. Heat energy is the energy in on which the whole thermodynamics is situated. In thermodynamics, what we will deal with some quantities like volume, temperature, pressure, heat energy, and work. So temperature and heat are two different things. Now I told you earlier. Uh, an example is to explain this thing, that you guys have maybe you guys have used microwave oven. When you put your hand in the oven, in the hot air of oven, your hand is not burned, but when you touch that metal rack of the oven, your hand instantly got burned. So what is this? Means both are on the same temperature, the air in the oven and the that metal rack in the oven. But when you touch the air, your hand is not burning, and when you are touching the metal rack, your hand is burning. So the answer is that they have really different energy contents. They have different powers of energy absorbing. They have different types of kinetic energy of molecules due to heat. And though the air is comparatively looks cool to the hands than metal, right? And that is why this is happening. So this you already know, conversion between Fahrenheit and Celsius. These are two temperature scale measurements, Fahrenheit and Celsius. So some formulas are there. If we know Celsius and 1 Fahrenheit, then we will do F equals to 9C by 5 plus 32 and vice versa. So about absolute or Kelvin scale. What is absolute or Kelvin scale? So the lowest possible temperature on Celsius scale is minus 273 degrees Celsius. So that minus 273 degrees Celsius is a Kelvin scale, which is 0 Kelvin or absolute zero. Okay, so in degrees it is minus 273 degrees Celsius, and in Kelvin it is 0 Kelvin. So basically absolute or Kelvin scale are the minus 273 degree Celsius. So now let's come to the our topic, next topic, heat. Heat is random motion of particles in the gas. Here is a diagram that you can show on your screen. These particles, these molecules are moving randomly. They are not following a definite path. So they have a degraded form of kinetic energy, means they are not possessing a type of continuous energy. So basically, in thermodynamics, we will deal with gas molecules only. So this is a schematic diagram of a container having gaseous molecules. Okay. So how heat can be transferred? So there are three mechanisms of heat transferring: conduction, convection, and radiation. Let's understand them briefly. What is conduction? Conduction is the conduction of heat through any metal or through any object. That you can see in this diagram. This is this side is comparatively hot, having higher temperature. We are denoting with TH. And this another side is having comparatively cold and having less temperature, and we are denoting this TC. So what is the property of heat? That heat flows from the higher temperature to the lower temperature. So heat flow will be from hotter section to the colder section, from pH to Tc. So this object which is in between these is the barrier, or we can see this is an object, or we can say a metal object, whatever it is. So heat is flowing through this. Okay, so when this phenomena takes place, we call this conduction. So the rate of heat flow has the formula: thermal conductivity into contact area into temperature difference above thickness. So it is Q over T equals to Ka delta T over D. So this is conduction, and this is the simplest example of conduction. When you fire a candle and put a metal rod from one side to the candle, then it is getting hotter and hotter, and the after some time the other side also gets hot. So this is the simplest example of conduction. Okay, next is convection. Convection is a typically complicated formula because we can't see the convection too happening. Like convection is basically the type of like liquid convection, vortex formation, sunspot, solar simulation, and from these examples now you guys can understand that convection is typically complicated phenomena. What is convection? Let's understand with some examples. So this is ocean currents. You can see in this diagram. In ocean, there are some currents generating time to time, and these currents we call convection currents. So this is the best example to see the convection. Another phenomena is happening down to the earth's surface. So inside the, or down to the earth's surface, going up to the inner shell of the earth, there also the phenomena happening, which is convection. These are convection cells which are producing the convection current, and this means this phenomena is called like plate tectonics. Okay, so the next one is radiation. Conduction we know, convection we know, and now let's start reading about radiation. So radiation is the basic phenomena in which everything that is radiating energy in the form of maybe in the form of temperature, maybe in the form of fire, maybe in the form of light, everything which is radiating energy, that is called radiation. So the method that energy from sun reaches to the earth is radiation. So the simplest example of radiation is the sunlight is reaching to the earth through radiation.
Ma'am?
Yes.
Ma'am, one general doubt, ma'am.
Yes.
Ma'am, on suppose, for example, I take a material. If that material, on what temperature it radiates their energy? What temperature, ma'am?
Sorry, I can't hear your voice.
Ma'am, suppose a material or something, a substance,
Okay.
it radiates some energy.
Okay.
On what temperature? Generally, what temperature it can radiate the energy, ma'am?
Okay, it depends on the that object type. What is that object? Different objects are radiating the energies on different temperatures. So there are specifically temperatures defined for every object. So we
Okay.
can't say a definite temperature for each object, that this is the temperature and each object starts radiating energy on this temperature. So this is not that.
Okay, ma'am. Thank you.
Okay, so this is the formula which we will follow in when we will derive the power of radiation. Okay, P equals to Q over T.
एक्सक्यूज मी मैम,
Yes.
मैम आपकी स्क्रीन शो नहीं हो रही है मुझे। जो आपने हीट वाला टॉपिक रहा था सिर्फ वही शो हो रहा है, उसके बाद शो नहीं हो रहा कुछ।
सभी के साथ ये समस्या है क्या, या फिर अगर आपको शो नहीं हो रहा तो आप एक बार वापस ज्वाइन कर लो।
ओके मैम।
हाँ प्लीज मुझे बता दिया करो अगर ऐसा कुछ है तो। The rest you guys can see the screen ना?
Yeah, we can see this. Not an issue.
Okay.
Yes, ma'am, we can see.
Okay. Okay. So in this screen now, you can see all the three in one frame. This is convection, this is conduction, and this is radiation. Okay. So now you can understand the difference between these three. Next, move to the next topic. Our topic is isolated, closed, and open systems. Okay. So, what is isolated system? In my language, if I explain, an isolated system is like a box of wood. When we put a box of wood on in sun heat, and we are just putting some chocolate inside, the chocolate will not melt for a long while, because a box of wood is comparatively absorbing less sunlight. Instead, when we will put a box of steel and we are putting a chocolate inside, and we are putting it in the sunlight, the chocolate starts melting soon. So these are the types of systems, and we will divide these or group these systems into three types. These are isolated, closed, and open systems. So in this slide there are something basic, which is system wall, and what are diathermic wall, what are thermally isolated, and what are thermally insulated, and what are adiabatic audit, and diathermic wall the hotter system to the colder one also, we can say that. So this is important thing. In isolated system, you can't exchange mass or energy with the surrounding. So the wall of an isolated system, what it must be? It must be adiabatic. Now a closed system can exchange energy but not mass. Energy can, in which energy can be exchanged. Okay, but in an open system we can exchange both mass and energy. So now these are the three systems in one diagram. This is isolated system, neither energy nor mass can be exchanged, but not mass. This is open system, both energy and mass can be exchanged. Okay, let's know more dynamics. So first, studying about zeroth law of thermodynamics, thermal equilibrium. Thermal equilibrium is if warm and cool objects are placed in thermal contact, is like a state of constant heat or temperature. Based upon that thermal equilibrium. What we are doing in this law, we have the three systems A, B, and C, or the three objects having temperature A, having temperature B, and having temperature C, we can say. When two objects A and B are at equilibrium stage, and A is also in equilibrium with C, then automatically the object B will be in thermal equilibrium with C. So this is the basics of zeroth law. What is it saying? It is saying if an object A is having thermal equilibrium with B and A is also having thermal equilibrium with another system C, then B and C both will automatically be in thermal equilibrium with each other. So the zeroth law of thermodynamics works the same way as temperature. This is the phenomena of temperature. Some thermodynamics variable we will study now because we are moving ahead to the first law of thermodynamics. So before studying the first law, we should know that there are some thermodynamics variables, some macroscopic or microscopic variables. The main variables are P, V, and T. Oh, the whole thermodynamics depends upon pressure, volume, and temperature. So if these variables are used to describe an equilibrium state of system, they are known as state variables. So pressure, volume, and temperature are state variables also, because we will use them to describe an equilibrium state of any system. Okay. There are two types of variables. We can categorize these variables into types: extensive and intensive variables. So extensive variable are those who depend on the size of the system, like mass, volume, entropy, etc. And intensive variables are those who do not depend on size of the system, like pressure, temperature, magnetic field, etc. Okay. And there are three types of processes also: isothermal process, adiabatic process, and free expansion. First of all, what is isothermal process? There are some more processes also. I will tell you later. What is isothermal process? Isothermal process is that in which temperature is constant. Just what we will do, we will put some gas in the heat bath or reservoir at any temperature, and we will not increase or decrease its temperature. So this is called isothermal process. Adiabatic process is that we are just increasing the pressure on that gas by any piston, then the gas is saturating or compressing. This type of process is called adiabatic process. And adiabatic pre-expansion is that at lowering the temperature, the gas is expanding, but there is no relation with its surroundings. Okay, the system is totally insulator. So this is adiabatic pre-expansion. So these are three main types of processes. Now, these are some vocabulary for thermodynamics. Isobaric, when we will call any process isobaric when pressure is constant. And when pressure is constant, the PV diagram will this. Uh, Pressure is constant, so just a straight line or a parallel line to the volume axis. Isovolumetric we will call isovolumetric when volume is constant, and when volume is constant, work should be zero, and the graph will be like this. temperature is constant and temperature
Ma'am, your voice is not clear. Guys, can you hear Monica, ma'am?
Yes, yes, ma'am. So much distortion in your voice.
It's not audible, ma'am.
Okay.
PV diagrams. Okay, let me understand. Let me make you understand these diagrams. When work is by the gas, W by the gas is area under the curve, means path moves to right from this side to this side. Okay, this is work by the gas. And when work is on the gas, path moves to left, means minus area under curve. So we will move from this side to this side, means to downwards. Okay, from this side to this side. So basically work on the gas equals to minus work by the gas. So these things we should also keep in mind. Now work from closed cycles is when the cycle is clockwise. Clockwise means from A to B and B to A. Then this area should be the this blue side, this circle. Okay, this is clockwise cycle. Then work is positive. Okay, when we will move counterclockwise from A to B and B to A, this side, okay, then work is negative, means negative of area. And when we talk about closed cycles, the change in internal energy will be zero, always zero. So change in internal energy is zero in closed cycle. Either it is work done by the gas or it is a work done on the gas. Okay, so this is example A. So students should answer. Consider an ideal gas undergoing the trajectory through the PV diagram, and this is the PV diagram. In going from A to B to C, we are moving from A to B to C. The work done by the gas is, and there are three options: greater than 0, less than 0, or equal to 0. So what should come here, A, B, or C? We are moving from A to B and then B to C.
Ma'am, it's counterclockwise. Then work done by the gas is negative.
Negative. So less than 0. So
Yes.
B should
Yes,
be
less
right.
than 0.
Okay. Okay. And another example is in going from A to B to C. Now what we are doing, we are going from A to B to C. The change of internal energy of gas is greater than 0, less than 0, or
Equal to 0. Equal to 0.
Equal to 0. Good, good, good. Okay. So let's move ahead. Now we will
Internal
talk
energy is
about
always 0.
thermodynamic work. Yes, equal to 0. Okay, I got it. Now, let us talk about the sign convention. Sign convention of thermodynamic work. Work in various processes. So, we will derive work in isobaric, isochoric, isothermal processes. Okay. So, you guys now know that work done by the system is positive. Okay, and work done on the system is negative. In cyclic process, clockwise we will consider positive work and anti-clockwise we will consider negative work. Now, reversible isochoric process gives work equal to 0. Why? Because in the isochoric process, volume is constant, so change in volume should be 0. So when change in volume is 0, then work is 0, because what is the expression of W? W is used to be PdV, pressure into change in volume. So when change in volume is 0, then work is also 0. So next is isobaric process. When we will talk about isobaric process, we will write work as W equals to P delta V, means P V2 minus V1. This is basically higher volume to lower volume, and pressure is the same. So P V2 minus V1. And these results hold for all materials, for all the types of materials. Either it is plastic, or it is steel, or it is iron, or whatever it is. Work done is always positive for expansion. When gas is expanding, we will consider the work done is positive. And it is negative for compression. When gas is compressing, we will consider the work done as negative. Okay, now we will talk about isobaric process from this graph, this diagram. So this is P, and isobaric process is happening. So we will write W equals to P V2 minus V1. So this is V2, the higher one, and this is V1. And when we will talk about isothermal process, so isothermal process looks like this graph, this slope. So the total area covered by this total area is the work done in isothermal process. So the expansion of work for isothermal process is written here, which is W equals to integral P dV equals to nRT integral dV over V. Why I am writing this P dV equals to this? Because P equals to nRT upon V. You guys know the ideal gas state equation, PV equals to nRT. So this becomes nRT, and integrating 1 over V with respect to volume, we are getting ln V2 over V1. So this is the work done for isothermal process, and we are talking about ideal gases. Okay, let's move ahead. And this is again example number C. So fastly you will reply these answers. We are considering a monoatomic ideal gas, and the gas state equation, you know, PV equals to nRT. Just consider n equals to 1. What work was done by the gas from A to B? So this is point A, this is point B, and when we are talking about A to B, then this whole area covered by A to B is the total work done. So anyone can tell me what is the answer of A? What work was done by the gas from A to B? Anyone? Okay, let me solve this here. So what we will consider, we will just consider this whole area, from here to here, this area we will consider, and we will apply now the simplest method I am telling you guys, which is just subtract 75 and 25, which is 50. So we are getting our pressure. What is that? That is 50 kilopascal. Okay, and P delta V. So delta V is change in volume, which is 0.6 minus 0.2, that is 0.4. So 0.4. And when you will multiply this, what you are getting? You are getting 20, and this is 20 kilopascal meter cube. So pascal into meter cube is joule, and we are getting 20 K. So what we are getting? We are getting 20,000 joule. So the answer of A will be, what will be the answer of A? That will be 20,000 joule. So let me write this. This is 20,000 joule. So can you guys understand this concept?
Yes, yes, ma'am. Very well.
Yes, ma'am.
Okay. Now, what heat was added to the gas between A and B? So, students, when the examiner asks the heat added to the gas, the answer will be the same of work done. So, the work done is 20,000 joule, na? So, the heat added also will be 20,000 joule. Now the C is what work was done by the gas from B to C. Now you can answer. Just tell me what will be the answer of C. Fastly.
Ma'am, 10.
I think it's ma'am 10,000 joule.
Okay. Next, D.
Yes, minus 10. What is it? The gas between. Ma'am, it's also 10,000 joule. I think heat added is
No,
the same
wrong.
as
No.
work done.
That is not
Okay,
an
why
isothermal
it
process.
is? Okay, it's
A to
isochloric
B
process.
is an isothermal process and it is an isochoric process.
Yes, ma'am.
Okay,
Sorry.
so just me write down all the answers. So you will do these things after I'll provide the same PDF to you, and the recording of the lecture will also be provided to you guys, so you can see these answers later on also. Okay.
Sure,
uh,
ma'am.
Basic concept is that. Okay, now let's move to the next slide, and two questions are also left. What was total work done by the gas in cycle? So total work done will be we will just derive A to B, work done A to B, then B to C, then C to A, and we will just add them all, and we will get 10,000 joule. And total heat added, so we will do the same, QA to B plus QB to C plus QC to A. And heat added or heat absorbed, how we will know this thing? So this is, we will add heat Q in, means inside we are giving the heat through this process A to C and through this process A to B. But B to C is that process from which the heat is coming out. Okay, so we are giving the heat from these two processes, and from B to C we are getting the heat out, and thus we are getting Q in equals to 35,000 joule, Q out equals to 25,000 joule. So the total heat will be 10,000 joule only. I guess you guys can understand this phenomena. Okay, now work done by the gas. Basically, work is force into distance. So force into distance covered by this force is work. Force is pressure into area. So pressure is P, area is A into delta Y. Delta Y is the mean length changed. So A delta Y is becoming delta V. So what we are getting, W equals to P delta V. So this expression is coming from here. Let's move to the first law of thermodynamics. So first law of thermodynamics is Q equals to delta U plus W. Change in internal energy plus work done is equal to the total heat. This is the first law of thermodynamics. So in the first law, we will use the differential form only, because we will apply this differential form in many phenomena in thermodynamics. So the differential form of first law is du equals to dq minus dw, and this du, dq, dw, these are exact differential, and du is an exact differential because u is a state variable. Okay, and dq and dw are inexact differential because q and w are not state variables. I've told you this thing earlier. Okay, these are some exact differentials and so on. Okay. Heat capacities. What is heat capacity? Heat capacity is change in heat with respect to temperature. So Ci equals to dq over dt I. One cannot use the partial form. Why? We can't write delta Q instead of dq because dq is an inexact differential. These are some small things you guys should know. So I've added all these things in my lecture. Heat capacity is at constant volume is CV, which is CV equals to dq over dt at constant volume. I can hear some voice. Okay, Jitendra Ahlawat. Heat capacity at constant pressure Cp. Cp is dq over dt at constant pressure, and enthalpy is H equals to U plus PV. So enthalpy, entropy, these things we will study later. So we know about two specific heat Cp and Cv. So the ratio of these specific heat is gamma equals to Cp upon Cv. Okay. For a reversible process, du is dq minus pdv, and for adiabatic process, we know dq equals to 0. So this dq is gone. So du equals to minus pdv. Okay. All these things are for ideal gases. Okay. All these things are for ideal gases. We are considering the gas as an ideal gas. So for an ideal gas, U equals to U of T, because internal energy is a function of temperature, so that Cv equals to du over dt. Now Pv equals to nRT. We know that Pv equals to nRT, and H equals to U plus Pv. So U is the function of temperature, and P and V are state variables. So enthalpy is also will be the function of temperature. So H equals to H of T. So what Cp can be? Cp also can be dH over dt. This is the Mayer relation. You guys have studied it in the 11th standard. Cp minus Cv equals to nR, which is known as Mayer equation. And this also holds for an ideal gas only. If we put n equals to 1 mole or 1 kilomole, so Cp minus Cv will become R. Okay, you know Cp and Cv are specific heats. So adiabatic process follows dq equals to 0, so du equals to minus pdv, and these are some formulas. So these are some formula slides you can see later on. Okay, so this is work done in adiabatic process. There are two methods to derive this. First one is direct integration. So for a reversible adiabatic process, we know PV raised to the power gamma equals to K. And as the process is reversible, so W equals to integral of PdV. What we will do? We will just put the value of P, which will be K upon V raised to the power gamma, and we will just do the integration. What we will get? We will get W equals to minus 1 upon gamma minus 1 P2 V2 minus P1 V1. Now for an ideal monoatomic gas, gamma equals to 5 by 3, so it will be W equals to minus 3 by 2 P2 V2 minus P1 V1. Okay. The second method to derive the work done in reversible adiabatic process is from first law of thermodynamics. So we know that W equals to Q minus delta U, and in adiabatic process Q equals to 0. So W will be minus delta U, and delta U is used to be Cv delta T. So we can write it as NCV T2 minus T1. So W will be minus NCV T2 minus T1. We know that the state equation of ideal gas is PV equals to nRT. So W will be minus Cv upon R P2 V2 minus P1 V1, and just at last we will apply the Mayer relation, and we will put the value Cp and Cv, and we will apply that ratio gamma. So what we will get? We will get the same relation. So these are the two methods to follow to derive the work done for a reversible adiabatic process. Okay, so these are the reversible processes for an ideal gas. In a table, I have summarized them for adiabatic process, isothermal process, isobaric process, and isochoric process. Isothermal process having T constant, isobaric P constant, isochoric V constant, and in adiabatic process Q is 0. Okay, so in adiabatic process the state equation will be PV gamma equals to K, where gamma is Cp upon C1. Work done will be this. The isothermal process follows the work done this. Isobaric process W equals to P delta V, isochoric W equals to 0. So this is the table you guys can remember or summarize in your notes also. For that you can just read them and solve the questions. So just let us move to the second law of thermodynamics. Basically, heat does not have voluntarily flow from cold to hot. We know that voluntarily heat can't flow from colder section to the hotter one. Or all heat engines have E less than 1, means they cannot convert all the heat into work. We know that some heat is wasted always. So this is the basics of second law of thermodynamics, that how can we make a heat flow from colder section to hotter one. So this is basically second law of thermodynamics, in which we will follow the concept of entropy. So here a new phenomenon is coming, which is entropy delta S equals to delta Q over T. And entropy is basically the measurement of disturbance. Basically it is a thermodynamic variable, and when any system is reversible, the initial and final state entropy used to be 0, and when it is irreversible, then final state entropy is always greater. So second law follows two statements, Clausius and Kelvin statements. These are the two statements. I know you have read them in earlier classes also, in 11th standard or in graduation level also. So these statements are just following the concept of change in entropy. What Clausius statement is following, it is saying that delta S universe is equal to Q2 upon T2 minus Q1 upon T1, and if Q1 and Q2 are equal, then it is less than 0. On what is Kelvin statement is saying, it is saying delta S universe is equals to minus Q over T, which is also less than 0. So in this diagram, I have shown the heat engines. Now we will talk about heat engines in our next slide. So these are basic two statements of second law of thermodynamics. So let's come to the cyclic heat engine. The concept of cyclic heat engine is coming out from the second law of thermodynamics, which is delta S universe equals to delta S plus delta S dash, where S is entropy of system and S dash is surrounding. Delta S means the entropy of system is changing. Delta S dash means the entropy of surrounding also changing. And the entropy of universe is increasing by time. Okay, so we can't decrease the entropy of system by any of the method. So cyclic heat engine will follow the same concept. After one cycle, delta S universe will be greater than equal to 0. After another cycle, it will also the same. So this is the heat engine in which there used to be a hot reservoir and a cold reservoir, and you know that heat flows from hotter to colder section. So what is the mechanism is that when the heat is flowing from this side to this side, some work we are getting by some mechanism, we are getting some work. So this is the basic phenomena of any cyclic heat engine. Basically heat engines are categorized into two parts: real heat engine and impossible heat engines. So these are shown in these diagrams. Real heat engine are those in which QH equals to QC plus W. QH is the energy for hotter section and QC is the energy for colder section. And impossible engines are like we are getting the heat from hot reservoir and we are converting all the heat into work, and QC we are getting always 0. So this is the impossible thing. We can't convert all the input into output. There is some wastage along with any process. So this is the model heat engine in which Q hot is used to be W plus Q cold. So Q hot minus Q cold equals to W. So what goes in must come out. This is the basic phenomena of model heat engine. The efficiency of heat engine is used to be E equals to W upon Q, where Q cold, I have told you earlier, is waste energy, waste money, and so on. So we know that E equals to W upon Q, and we write W as Q hot minus Q cold. So it is E equals to 1 minus Q cold over Q hot. This is the simple expression for the efficiency. Real engines have the efficiencies between 0 and 1. Okay. So next, move ahead towards Carnot cycle. The very best theoretically possible heat engine is Carnot cycle. And in Carnot cycle, we write the efficiency of Carnot cycle as E Carnot equals to 1 minus T cold over T hot. And we will put all the temperatures in Kelvin scales. We will not use the Celsius scale here. So this is the schematic diagram of Carnot cycle. A Carnot cycle have the 4 processes. The first one is isothermal expansion. We will start with point A. Any cycle can start with point A from this point, and this point having the temperature TA and volume BA and pressure PA. Then we are expanding it isothermally. We are coming from A to B. Okay, we are coming from A to B, and this is isothermal expansion. Okay, this is isothermal expansion, and this is the second process. On point B, now we will start the adiabatic expansion. B to C is adiabatic expansion. So the gas will expand now adiabatically, and we will reach to the point C, here. Now we are having some output or QC now. So the third process starts from here, which is isothermal compression. Now we will compress the gas isothermally and we will reach up to point D. So C to D is isothermal compression, and the last fourth one is adiabatic compression from D to A. So this is basically any Carnot cycle follows this path, and this is the working phenomena of Carnot cycle. Carnot efficiency, you guys know that E equals to QH minus QC upon QH, and it is only valid for ideal engines. What is that? TC over TH equals to QC over QH. If any question says that consider an ideal engine, then you can use this formula. TC over TH equals to QC over QH. So basically, Carnot efficiency is when we write in a format, then we will just put into 100%. Like we are getting 3.1, the value of E, then we will write 31% of Carnot efficiency. We are getting 0.31, then we will write 31% of Carnot efficiency, and so on. So the input temperature is TH, heat input from here, and the output temperature is TC. We are getting the heat output from here. And Carnot explained some phenomena. Like by comparing the work done by the gas in first two process, the work done on gas in final two process is difference in area 1, 2, 3, 4, having the 4 different areas. So we are getting the 4 different values of W, the work done. And delta U is always 0 because Carnot cycle is an cyclic process, and in cyclic process there is no change in internal energy. Okay, so this thing you know already. This is the Carnot impossibility. What is that? E is, if E equals to 100%, let us assume any Carnot cycle having the 100% efficiency, then delta U equals to 0. And if delta U equals to 0, then delta S equals to 0. So is that possible to have delta S equals to 0? Like the change in entropy is 0? No, that is not possible, because we know from second law of thermodynamics that the entropy is increasing and we can't decrease this. So delta S should not be equals to 0. Delta S can't be equal to 0, and that is why the efficiency of any Carnot cycle can't be equal to 100%. So this is the Carnot impossibility. And okay, so delta S should be 0 only occurs at absolute 0, which is impossible to achieve. So no device can transform a given amount of heat energy into work. Automobiles have efficiencies in the range of 20 to 35%. Okay, the automobiles which we use having the efficiency between 20 to 35%. This is the next example. What is the maximum efficiency possible of an engine that operates between 500 degrees centigrade and 250 degrees centigrade? So efficiency, you know that E equals to that formula 1 minus QH upon QC or TH upon TC. You will just put these into Kelvin scale, 500 degrees centigrade and 250 degrees centigrade, convert them into Kelvin scale and derive the answer. Can anyone tell me what will be the answer? Please unmute your mics and reply fast. Hello.
Hello.
Yes.
Ma'am, I need to convert 500 degrees Celsius to Kelvin scale, ma'am.
Yes. Because we will use Kelvin scales in thermodynamic phenomena only. We don't use directly them into Celsius scale.
Ma'am, when 500 degrees Celsius convert to Kelvin scale, it took 773
Yes.
Kelvin, ma'am.
Yes.
773.
Yes. Okay. So you can derive the answers. The answer will be 32%.
77. Ma'am?
Yes.
Ma'am? Hello, ma'am.
Yes. I can hear you.
Ma'am, if T2 by T, okay, T2 by T1 is equal to, I think, 33%. Nearly.
Approximately 30, nearly 33. So the answer will be 32 to 33%.
Then efficiency is, but ma'am, efficiency is equal to 1 minus T2 by T1. So 1 minus 33, how can we then?
No. I think you are mistaking somewhere. Check again. Okay, I'm moving ahead. This is very easy. You can do this later on. Okay, now the next example is the exhaust temperature of a heat engine is 240 degrees centigrade. The engine produces 500 joule of work and has a Carnot efficiency of 45%. So what is the temperature of heat source? So here we will have to derive TH, means the temperature of higher hot reservoir, or B is what heat is extracted from heat source. so QH, and what heat is delivered to the cold reservoir, QC. So these three answers we will derive, and you will derive these three answers. So बताना मुझे क्या आंसर्स आ रहे हैं, एंड ये आंसर्स मैं आपको दे रही हूँ 930 केल्विन, 1100 जूल एंड 610 जूल्स. तो ये आंसर्स होंगे, आप चेक कर लेना और फिर बताना. Okay, now let's
Okay,
move
ma'am.
ahead to the refrigerators. Refrigerator is an inverse process of Carnot cycles. Okay, what we will do here, we will just extract some heat from the cold reservoir and we will apply some work. We will put an engine here and we will get output from here, like the heat what we are receiving into hot reservoir is our output now. So the input becomes QC, the output becomes QH, and we are applying work also. So this is the basic phenomena of refrigerator. So these refrigerators are also categorized into two groups: real fridges and impossible fridges. Real fridges are those which follow the same phenomena. Some heat we will add, we will put some work, and we will get some output. So QC plus W equals to QH. And impossible fridges are those in which we will put some heat and all the heat is converted into our output without doing any work, means W should be 0. So this is the impossible phenomena. By any of this situation, we can't do this, like we will not do any work and we will get some output. Okay, so the real fridges are these and impossible fridges are these. This is the basic phenomena of refrigerators. When we will talk about efficiency of Carnot cycle, we write E, and we will talk about efficiency of refrigerator, we write kappa, COP, which is Q upon W. And the most efficient is Carnot refrigerator is COP cooling is less than COP Carnot. So highest COP for small T differences. These are some basic things. Okay, these are some questions which I have taken from previous year papers of CSIR-NET and GET. So I will provide you the answers here only. The question is that delta W be the work done in quasi-static reversible thermodynamic process. The following statement about delta W is correct, and there are 4 options. So the question is, in any quasi-static reversible thermodynamic process, delta W is denoting by the work done. So what is the correct statement about delta W? Delta W is perfect differential if process is isothermal. Delta W is perfect differential if process is adiabatic. Delta W is always perfect differential, and delta W can't be a perfect differential. This is a question from NET December 2012, and here is the answer. Work done is perfect differential in adiabatic process. So when we will talk about adiabatic process, we will just put work done as a perfect differential. Yes?
Ma'am, what is quasi-static?
Okay. Quasi-static process is like quasi-static process is that process which is moving ahead gradually when we are not talking about equilibrium but near to the equilibrium. Any system that starts reaching to the equilibrium but anyhow it is unable to reach to the equilibrium, then that state is called quasi-static. Near to the equilibrium, next to the constant. Okay, near to the constant is a quasi-static. I will explain it in my further lectures, don't worry. The second question is, in the thermodynamics, a process is called reversible. Then there are 4 options. When a process is called reversible, a process is reversible when surroundings and systems are in equilibrium. So this is an easy question. Next question is, a Carnot cycle operates on a working substance between two reservoirs at temperature T1 and T2, where T1 is greater than T2. During each cycle, an amount of heat Q1 is extracted from the reservoir at T1 and Q2 is delivered at T2. So which of the following statement is incorrect? Now you know all about the Carnot cycle. The question is saying that a Carnot cycle is working between two temperatures where T1 is higher. We are having some amount of heat Q1 we are extracting at temperature T1, and we are delivering some amount of heat Q2 at temperature T2. So amongst them A, B, C and D, which will be the incorrect statement? So you can read all the four options. First one is work done in one cycle is Q1 minus Q2. Q1 upon T1 equals to Q2 upon T2. Entropy of hotter reservoir decreases. Entropy of universe increases. So tell me what should be the answer? This is the question from GET 2011. Okay, the answer is C. Entropy of hotter reservoir decreases, because the entropy can never decrease. Okay, so a simple question was this, and these types of simple questions come in exams, and students got confused like what to do and what not. Just we think with stable mind and answer the questions. Okay, next question is, a given quantity of gas is taken from state A to C. This is the diagram. A to C reversibly by two paths, A to C directly and A to B to C, as shown in figure. During A to C, work done by gas is 100 joule and heat absorbed is 150 joule. If during A to B to C, work done by gas is 30 joule, then the heat absorbed will be. And this is the question from NET December 2012. The question is saying that there are two paths from going from A to C. We can follow the path directly. We can come A to C directly, or we can go through B, A to B and B to C. Okay. When we will follow the first path, A to C, work done will be 100 joule and heat absorbed is 150 joule. And we will follow the second path, work done will be 30 joule, then what will be the heat absorbed? So the question is simple. Answer is even simple. We will follow the first law of thermodynamics, which is dq equals to du plus dw, and dw1 we know 100 joule given, so we can derive du. Okay, du will come 50 joule. What we will do, we will just put the value of du for the second path and we will get dq. We will get 80 joules. So correct option will be D. Correct option will be B, 80 joules. The question was simple and the answer was even simple. Okay. Next question is, a Carnot cycle operates as a heat engine between two bodies of equal heat capacity until their temperatures become equal. If the initial temperature of the bodies are T1 and T2 respectively, and T1 greater than T2, then their common final temperature is. And this question is from NET December 2013 paper, and the answer is given. As Carnot cycle is reversible cycle, so entropy is 0, obviously. Let the equilibrium temperature be T, then delta S, what will be delta S? Delta S will be C integral dt over T. You know that delta S equals to dq upon T. So we can write this, and is equals to 0. So what you guys will do, you guys just integrate this and you can derive this answer, T equals to under root T1 T2. So the correct option will be option number C. Okay. Next question is, When a gas expanded adiabatically from volume V1 to V2 by a quasi-static process. I've told that quasi-static process is the process where we can say it near to the equilibrium. It cools from temperature T1 to T2. If now the same process is carried out adiabatically and irreversibly, then T2 dash is the temperature of the gas when it has equilibrated. Then, and there are four options. The question is saying that a gas is expanding adiabatically, okay, by a quasi-static process, and we are cooling this from T1 temperature to T2. Now, the same process, the same gas is carried out adiabatically and irreversibly, and now the temperature is T2 dash. So at equilibrium position, we will derive the relation between T2 dash and T1 D2 and V1 V2. So basically this question is from CSIR-NET December 2014. It looks complicated, but it is not. The answer is C. T2 dash will be greater than T2. How? And here is the answer. We will follow the first law of thermodynamics, which is Q equals to delta W plus 0. And in adiabatic process, Q is supposed to be 0. So 0 equals to delta U plus W. So delta U is minus W now. And the W in adiabatic reversible process is greater than W in adiabatic irreversible process. So we can write directly T2 dash is greater than T2. So irreversible process, the temperature of irreversible process is always greater than the temperature of reversible process. These three things you should note down. This happens in adiabatic, reversible and irreversible processes. The next question, and it has the answer also. The heat capacity of a refrigerator is 4.2 kilojoule per Kelvin. The minimum work that must be done to lower the internal temperature from 18 degree to 17 degree when the outside temperature is 27 degree. And there are four options. This question is from NET December 2015. So heat removed from inside of refrigerator is Q2, which is this heat capacity is given now 4.2 kilojoule per Kelvin, this heat capacity. So it is Cp 4.2 and delta T means difference in temperature. This is 18 degree to 17 degree. So we will get 4.2 kilojoule. Now heat given to outside atmosphere Q1. We know that for an ideal reversible process, Q1 upon Q2 equals to T1 upon T2. I told you this thing earlier. So Q1 equals to T out upon T in. Just put all these values. And for minimum work, Q1 minus Q2, you know this expression. Just subtract this and you will get 0.14 kilojoule. So the answer will be D. Okay. So these were some questions from previous year papers related to the today's lectures. Any questions, any queries, you can ask now.
Hello, ma'am.
Yes.
Can I ask you a general question, not about that
Yeah.
subject?
Yeah, sure.
Ma'am, is refrigerator and air conditioner are increase the heat of the world? Is it right or not?
Yes, of course, it is right.
But ma'am, if we
These are the
consider,
main causes of global warming.
but ma'am, if we consider world as a closed system, then work done in system
No,
is
word is, we are considering in thermodynamics word as a surroundings.
okay.
How can we consider world as a closed system? We can consider earth as a closed system. It is closed by its atmosphere, but we are destroying the atmosphere, and that is why we are getting these temperature increment every year.
Okay, but ma'am, our house or a room not
Mhm.
a proper closed system, na? Then it leakage in heat. So cold air is blow outside. So the condition
Mhm.
will be same. Heat first of all when
And the change in entropy can never be zero, because at every time we are running the ACs or refrigerators, they are doing their work and they are, generating some unwanted gases and particles. Those are disturbing the health of environment, and in that manner entropy is changing. So
okay,
entropy always changes in any format. Entropy always changes.
always okay, got it.
Okay.
Hello, ma'am.
So if yes, yes,
Ma'am, I have a general doubt, ma'am. Ma'am, what is the
yes.
difference between isothermal process and adiabatic process?
The basic difference is their state variables. In isothermal process, we consider temperature as a constant, and we can't consider temperature as a constant in adiabatic process, because in adiabatic process, as we are not giving any heat or extracting any heat, so there is Q equals to 0. So this is the main difference between isothermal and adiabatic
Isothermal
process.
process, temperature is constant. In
Yes, yes.
adiabatic process, there is no heat flows from that particular.
Yes, yes.
Okay, ma'am. And then, ma'am, what is the difference between monoatomic gases and ideal gases?
Ideal gases, actually monoatomic gas is the gas having monoatom,
Okay, ma'am.
atom alike. Like if we are considering hydrogen gas, then we are considering only hydrogen molecules or hydrogen atoms, then it is monoatomic gas.
Okay,
So hydrogen gas may be an ideal gas. Actually, it is real gas, and there are no ideal gas in the world right now.
okay, ma'am. Is there is any example for ideal gas, ma'am?
No, no, no. Actually, in the present scenario, there
Okay,
is no gas defined as ideal gas, because it is hard to reach at those limitations of having ideal gases. In lab, we can prepare some ideal gases, but there is no use of those.
Yeah, Monica ma'am. But if you are speaking, you are asking about the monoatomic gas, na? So,
Yes,
like
yes.
monoatomic gases, like the inert gases, like we can say are helium, neon, argon, krypton, na?
krypton.
So these are basically the monoatomic gases. Okay, because they
Yes,
can
yes.
exist in nature in single
As
atomic form.
monoatomic format. Yes, yes.
Yeah.
Okay, ma'am. Yeah.
Okay, so the next few slides are about questions. So these are some practice questions you guys will do as homework I'm giving. So these 6 questions, all the questions are on Carnot cycle, work done, and all that. So thank you.
Thank you, ma'am.
Thank you, ma'am.
Ma'am, you can